This is the second of two videos about a structure of a data analysis. Remember from the first video that the steps in a data analysis start with defining a question that we care about and end with synthesizing and writing up results or creating reproducible code. The first few steps are covered in part one of the two videos, and in this video we'll cover the steps from exploratory data analysis to building a statistical model or prediction model, interpreting the results so that they can be communicated to other people, then challenging them to be able to evaluate whether the statistical modeling choices that we made were good ones, synthesizing and writing them up so that they can be easily communicated to other people, and then we'll talk a little bit about creating reproducible code. So remember that the question we were starting with was, can we automatically detect emails that are spam from those that aren't? We made it a little bit more concrete by asking, can we use quantitative characteristics of the text of the emails themselves to classify those emails as spam or ham, which are the emails that we want to be able to read? Unfortunately, we don't have access to all of Google's email servers, so we settled on this dataset that's available in the Kern Lab package in R. This dataset consists of about 4,600 emails and 58 quantitative characteristics of those emails. One of the variables that's measured is whether the emails are spam or ham as labeled by individuals who collected the data. Remember that since we're trying to perform a prediction in this particular case, we need to generate a training set and a test set. We did this by generating a random training set indicator that consisted of a set of coin flips, one for each of the 4,600 emails, with equal probability being for the training set or the test set. At the end of the day, this produced a set with 2,287 emails in the training set and 2,300 in the test set. Then we subsetted our original data set to create a training set and a test set. So the first thing that we're going to do is go over exploratory data analysis. We're going to go over all of these steps in much more detail during the course of the class, but I'm just going to show you a little bit of a flavor of how this would work on our specific example. In exploratory data analysis, we might look at summaries of the data, check for missing data, create some exploratory plots, and maybe perform some sort of exploratory statistical analyses like clustering. So the first thing that we can do is look at the training set. We're going to focus on the training set because we want to leave the test set aside so that we can see how our predictions work on that test set later at the end. The first thing that we could use is the names command. The names command, shown here, just tells us the names of the columns or the variables that are included in the data frame. Here we have quantitative variables for make, address, all, etc., and these are just the percentage of times that these particular words appear in the data set. We also see some cases where it says num and then a number, and that's the fraction of times that that number appears. Finally, we see the fraction of time that particular characters like square brackets, hashtags, or dollar signs appear in the data set. The last variable is type. This is whether the variable is spam or not spam, and that's what we're trying to predict in our analysis. So the next thing that we can do is use the head command to see what these variables look like. So each of these variables is a percentage, at least for the word variables like make and address. So here we're able to see what the first few variables look like. In the first email, there's 0% of the words are called make. In the second email, 0% again, and in the third email, it's about 15% of the words are called make. So we can use these commands like head to get an idea of what the data set looks like by looking at just the very top of the file. We can also start to look at some summaries of some of the variables. So for example, we can use the table command like this, table, of the type variable by accessing it from the data frame with the dollar sign. And we see that about 1,300 of the emails in the training set are not spam, and 906 are spam. We can also start to make some basic plots. Again, don't worry too much about knowing the exact commands and how they make certain kinds of plots right now. We'll cover that later in the class. But this gives you an idea of some of the things that you can do with exploratory analysis. So here, we're plotting the percentage of times that we see a capital letter in the data set versus the type. Here's something that might jump out at you right away when you look at this plot. There are values here that are above 1. So that's something that we might want to explore further in our analysis. If you can't see the values too easily using the previous example, what you can do is you can actually calculate the log of the values and then make the same plot. This kind of transformation is commonly done in exploratory analysis, and it makes it a little bit easier to see the difference in the distribution between the spam and the non-spam values. We'll talk a lot more during the class about different transformations, but again, this is just to show you an idea of how it works. We can also make plots that show the relationship between predictors. Here, we're plotting the first 4 columns of the training set by accessing those columns here with this subsetting command. We're taking the log of those values and adding 1, and again, plotting them versus each other. The way this plot works is that you see here the percentage of the times that make appears in the email versus the percentage of times the address appears in the email in this plot right here. It's the same plot right here, but with the axes reversed. You can see these plots appear for all of the different examples in the data set. Next, you might perform some exploratory analysis, like clustering. Here I've performed a hierarchical clustering of the first 57 columns of the training set for all of the variables. Again, don't worry too much about what hierarchical clustering is at the moment. You can just think of it as this is an analysis that tries to put variables that have similar patterns close together. And then we can plot this cluster dendrogram as you see down here. So variables that are very close to each other in this dendrogram are variables that have very similar patterns of observations across all of the different emails in the study. This is a little bit hard to see, so you might again perform some sort of transformation to make it a little bit easier to see. In this case, we might take the log of the values, just like we were doing before. And we might focus on the first 55 values, since values 56 and 57 correspond to not percentages, but actual numbers calculated. Here in this dendrogram, it makes it a little bit easier to see the clusters of variables that go together. For example, you might see that email and address are very close to each other in this clustering. Don't worry about the details, but this is how the typical exploratory analysis works. You make plots, perform transformations, and identify potential problems with your data analysis. Once you've performed a thorough exploratory analysis, it's time to move on to statistical prediction or modeling. It should be informed by the results of your exploratory analysis, but you should have thought in advance what type of methods or models you might think to apply in the ideal case. The exact methods that you'll be using depend on the question of interest, and we'll talk about a variety of different statistical methods you can use for different questions. Transformations and processing you might have done to the data during your exploratory or pre-processing of the data should be accounted for when necessary in the downstream analysis. For example, if you fit a model on the log transform values, you should pay attention to how this might change the modeling assumptions that you're using in your data analysis. Recall that measurements of uncertainty should always be reported for statistical models and predictions. Next, we're going to consider statistical prediction and modeling for our specific data set. You don't have to understand all the details of the R code that I'm going to be describing here. I've just included it so you can see how the process might work for a typical data analysis. I will go over the general idea of what we're doing here. Basically, what we're doing is we're taking the 55 variables that correspond to a fraction of times a word, character, or number appear in an email, and we're going to write a loop that goes over all of those 55 variables and fits a predictive model that relates whether an email is spam or ham to the fraction of times that that character or word appears in the email. Then we're going to calculate the error rate for those predictive models and pick the model that has the minimum error rate. In this case, it's variable 53. We can then go back to the data set names of the training set and identify what is the name of the variable that gives you the minimum error rate. In this case, it's character $. This makes sense because if there are a lot of dollar signs in a particular email, it probably is spam. We next need to get a measure of uncertainty. The way that we do that is first calculate our predictive values for our model that relates the type of the email, spam or ham, to the fraction of times that $1 appears in that email. And then we apply that particular model to the test set. This is the test set that we left out when we were building our training set, so we'll be able to evaluate how well our prediction works in a new data set. We can then make a table plotting our predicted results versus the results that occur in the actual test set, where type is the type of variable that occurred, whether it's spam or ham. So now we can look at this table and we can calculate how often we make an error. So in some cases, it was a non-spam email, but we called it spam. That happens 61% of the time. So most of the time, we're pretty good at detecting non-spam. On the other hand, sometimes an email is spam, and we call it non-spam. We're not very good at detecting spam because it's about 50-50 whether we detect a spam email. Overall, we can calculate the error rate by adding up the number of mistakes we make and dividing it by the total number of emails that exist. It turns out that we have about an error rate of about 22%, which for this specific data set isn't necessarily that great, but that's because we've only used one particular variable in our model. We next need to interpret the results. Here it's critical that we use the appropriate language. If you've done a descriptive analysis, you should use the words like describe rather than variables that include some description of a prediction or an inference. When you're doing an inference, you might want to use words like infers, correlates with, or is associated with. These are all words that suggest that you performed an inference. If you've performed a causal analysis, you might use words like leads to or causes. Use these words with caution because if you've performed an exploratory analysis, a descriptive analysis, or an inferential analysis, it's very unlikely that you can ascribe a causal change in the relationship. If you've done a predictive analysis, you might use the word predicts. It's important to try to explain the associations, causes, or descriptions that you've observed in your data set. You want to do this in plain English, and the goal is to use units and descriptions that can be easily understood by non-technical audiences. You should also interpret coefficients or predictive models so that people can understand exactly how those models work. You also need to report and interpret measures of uncertainty. So in our example, we might say something like, the fraction of characters that are dollar signs can be used to predict if an email is spam. You might also say something like, anything with more than 6.6% dollar signs is classified as spam using our predictive model. More dollar signs always mean more spam under our prediction. In other words, as the number of dollar signs increases as a fraction of the total characters, we will be more and more likely to call it spam. We should also report measures of uncertainty that say things like our test set error rate was 22.4%, and we calculated this error rate on an independent data set from the data set used to build the predictive model. All of these are interpretations that explain the quantitative tools that you used. Next, you should challenge your results. You should challenge all steps, from the question that you asked, was it the right question? Could you have made it more specific? Could you have made it more general? To the data source, was it the right data? Did you get the right sample? Is it sampling from the right population? To processing, whether you did the transformations correctly or identified variables that might be problematic correctly. To the analysis, did we pick the right predictors, and so forth. And finally, to the conclusions and the interpretation. Are you interpreting too much into your models and trying to say something that you weren't able to say? You should also challenge measures of uncertainty and point out possible other sources of uncertainty that you didn't consider. And challenge sources of terms to be included in the model, and think of potential alternative analyses. By doing these steps yourself, you will be able to explain to others why you think your analysis is either strong or weak, and be able to help people make decisions on the basis of your analysis. Next, you will need to synthesize and write up the results. A critical component of this is leading with the question. Don't start with the statistical models that you used or the data set that you have. Start by just stating the question that you're trying to answer and how you're going to go about answering it. You should summarize the analysis that you've performed into a story that starts with a beginning and then explains how you performed all the analysis and ends with a conclusion. Don't include every analysis that you've performed. You should only include it if it is needed for the story or if it is needed to address a challenge. In particular, it's a common mistake in data analysis to order the analyses in your write-up by the order in which you did them chronologically. Instead, you should order them according to how they contribute to the story so that it makes it easy for the person to follow along with what you did. Since you may have tried multiple things and gone down multiple wrong paths in doing your data analysis, ordering them chronologically can often lead people to be confused about what you've done. Make sure you include pretty figures, and by pretty I mean figures that have big enough axis labels, captions, and so forth, so that people can follow along with the story as well. Your figures should be include just enough information to carry the story, but not so much that they're confusing or hard to read. In our example, you might want to lead with the question, can I use quantitative characteristics of emails to classify them as spam or ham? Then describe the approach. We collected data from a repository at UCI and created training and test sets that were independent. We then explored relationships between variables and chose a logistic model on the training set based on cross-validation. We applied it to the test set and got 78% test set accuracy. You should also include an interpretation of your results such that the number of dollar signs seems reasonable, because if you have emails that say things like make money with Viagra, dollar sign, dollar sign, dollar sign, they're likely to be spam. You should also challenge your results. 78% on this data set isn't that great. You can detect email a lot better than that, and most email companies do. Then you could explain ways that you could improve your analysis, like I could use more variables, or I could try other potential analyses, like why did I use logistic regression? I could have used a different type of analysis to build our predictive model. The last step in a data analysis is to create reproducible code. So this is an example that we've used today in creating this predictive model. This is what's called an R Markdown file, which we'll talk about more later, which includes information about the analyses that we performed in the form of R code, as well as the descriptions of what we've done in terms of the slides that we've used to produce this analysis. By creating reproducible code, you'll be able to communicate both the analyses that you performed and the exact way in which you performed them, so that other people can try other things and see if they work better. Once you've completed your reproducible code, you're ready to communicate your analysis and share your findings with the world.